Dear students, let's move further into the topic mechanical properties of solid. In the last lecture, we have studied about the stress and strain. There are three types of strain and three types of stress: longitudinal stress, volume stress, and shearing stress. Similarly, there are three types of strain as well: longitudinal strain, volume strain, and shearing strain. Now, let's study the new topic, Hooke's law. Hooke's law is a result, it is basically a result of the experiment in which the scientist Robert Hooke had taken one wire, and that wire is subjected to a stress, means its one end is attached to a load. Obviously, when we attach one load to the lower end of the wire, it will get elongated. So stress is applied to it. There will be a production of strain inside the wire. So stress and strain. The moment when what will happen when we go on increasing the load to the lower end of the wire, you will find that the strain produced inside the wire will also increase. When you go on adding a load, when you go on stressing it up, this wire will go on elongated. And a time will reach when the wire will break. So it is the result of Hooke's law is a result of this experiment in which the scientist Robert Hooke had taken one wire, and that wire is subjected to a continual increment of the stress. So what he found that when we go on increasing the stress, strain also increases. Strain means change in length per unit original length. So the strain produced in the wire will also go on increasing. So that is why the law states that within the elastic limit, means before the wire gets break up. So within the elastic limit, stress is directly proportional to strain. As stress increases, elongation will go on increasing. So you can say that as stress increases, strain will also increase. So statement is within the elastic limit, stress is directly proportional to strain. And we can write it as stress is proportional to strain. Remove the proportionality sign, you'll have to put some constant over here. So it will become stress upon strain is equal to some constant. And this constant is called as modulus of elasticity. As we all know that there are three types of stress and strain. So this modulus of elasticity is also of three types. We had considered the change in length, means longitudinal stress and strain. We had considered the change in size, means volume stress or volume strain. Then we had considered the change in shape, means shearing stress and shearing strain. So based on these three types of stress and strain, this modulus of elasticity, means this constant of stress to strain, is also divided into three parts. Whenever we are considering the change in length of the wire, so modulus of elasticity will be called as Young's modulus. When we consider the change in size of the object, then the modulus of elasticity will be considered as bulk modulus. And when we consider the change in shape of the object, then the modulus of elasticity will be considered as modulus of rigidity. So this ratio stress to strain, this ratio stress upon strain is constant, and this constant is called as modulus of elasticity. Let us see what is elastic limit. When we draw the graph between stress and strain, let us consider the graph. Here we have taken strain produced on the wire is along the x-axis and stress produced in the wire is along y-axis. So as we all know that within the elastic limit means before the wire get permanently deformed, that point till the stress and on the stress and strain curve till we get a straight line, means as we go on increasing the stress, strain will also increase. And up to this point, what will happen when you remove the loads, when you remove all the strain, this wire will again come back to its original length. Means the wire will not get permanently deformed. So this is called as elastic limit. So up to this point, up to the elastic limit point, stress is directly proportional to strain. So let us see how you can define elastic limit. The maximum value of stress up to which the stress is directly proportional to strain is called as elastic limit. It is the maximum stress which can be subjected to a wire till it get permanently deformed. Means up to this point the wire can get its original length. So it is called as elastic limit. Now let us quickly define the three modulus of elasticity that we have to study. Very first one is Young's modulus. Now here we just have to see the changes in the length of the wire. Here we have taken one wire over here of length L. Its one end is connected to the rigid support and its another end is connected to the load, or you can say stress or a force. So some mass is attached to the lower end, some load is attached so that the wire will get elongated. So let the elongation produced in the wire is small l. So based on this definition of modulus of elasticity, how we can define the Young's modulus? Here please remember that Young's modulus deals with the change in length, or it deals with the longitudinal stress and longitudinal strain. So ratio of stress to strain is called as modulus of elasticity. Here we will specify that ratio of longitudinal stress to that of longitudinal strain is called as Young's modulus. So let us see how to find out longitudinal stress. Longitudinal stress subjected to this wire is stress is always force per unit area, F upon A. But the force which we have applied is in terms of a mass. So mass into gravitational acceleration is force. So we will write it as mg. Force is mg. Upon area will be considered as the cross-sectional area of a wire. We know that wire is having cross-section as a circle. So area of a circle is pi r square. You can give it as equation number 1. Now let's calculate longitudinal strain. Strain is nothing but change in dimension per unit original dimension. Here the change corresponds to the change in length. So we will say that it is nothing but change in length per unit original length. As small l is the change in length of the wire and capital L is the original length of the wire. So longitudinal strain will have the formula small l upon capital L. Give this one as equation number 2. Then by the definition of Young's modulus is denoted as Y. It is equal to, it is a ratio of longitudinal stress to that of longitudinal strain. From equation 1, what is longitudinal strain? Stress? it is mg upon pi r square upon longitudinal strain is small l upon capital L. Now you just have to merge these things to get the final expression of Young's modulus, as this L will come in the numerator. It is mg L upon pi r square L. So here we have the final formula of Young's modulus as mg L upon pi r square L, where m is a mass attached to the lower end of the wire, g is gravitational acceleration, capital L is the original length of the wire, small l is the change in length of the wire, and r is the radius of the cross section of the wire. Now let us quickly solve two examples of your textbook based on the Young's modulus. Very simple one. Example number 6.1. See the statement and try to point out the given things from the statement. A brass wire of length 4.5 meter with cross section area of 3 into 10 raised to minus 5 meter square and a copper wire of length 5 meter with cross section area 4 into 10 raised to minus 5 meter square are stretched by same load. There are two wires. One wire is of brass and the other wire is of copper. The brass wire original length is provided, it is 4.5 meter and its cross section area is also provided. Similarly, for copper wire, length of the wire is original length is provided and its cross section area is also provided, and they are attached to the same load. They are stretched by the same load. Means the stress to which the wires are subjected are same. The same elongation is produced in both the wire. Change in length in both the wire is also same. Find the ratio of Young's modulus of brass and copper. So let us quickly write down the given thing. Length of the brass rod is 4.5 meter. Length of the copper rod is 5 meter. Similarly, area of a brass rod is 3 into 10 raised to minus 5 meter square and area of the copper wire is 4 into 10 raised to minus 5. And what else is provided? That both the wires are having same elongation. Elongation means change in length. So it is denoted by small l. Small lb is equal to small lc. C is for copper, B is for brass. Similarly, both the wires are subjected to the same force, same load. So force subjected to the brass wire is equal to the force subjected to the copper wire. Then we have the formula of Young's modulus as stress upon strain. It is F upon A into L upon small l. Then for brass wire, Young's modulus will be written as FB into LB upon AB into LB. And for copper wire, it is FC into LC upon AC into LC. Now ratio of brass to copper, because you'll have to find out the ratio of Young's modulus of the brass to that of the copper. So YB upon YC, when you take the ratio of these two equations, it will comes out to be equal to CFB into LB upon AB into LB, FC into LC upon AC into LC. So the numerator and C, it will comes out to be FB upon FC, capital LB upon capital LC, AC upon AB and LC upon LB, out of which FB and FC both are equal. So these two things are going to cancel. Similarly, same elongations are produced, so LC and LB will also get cancelled out. The ratio will become LB upon LC into AC upon AB, and all these four things are provided in the data. So just substitute the value as LB is 4.5, LC is 5, AC is 4 into 10 raised to minus 5 and AB is 3 into 10 raised to minus 5. My 10 raised to minus 5, 10 raised to minus 5 will get cancelled. 4 into 4.5 will become 18. 5 into 3 will become 15. 18 divided by 15 is 1.2. And unit of Young's modulus is, as it is a ratio of stress to that of strain, and since only stress is having a unit and strain is not having any unit, similarly this is the ratio of two Young's modulus, so this quantity is unitless over here. 1.2 is a unitless. Now let us consider the second example that we'll have to study. Let's see the statement first. Example number 6.2. A wire of length 20 meter and area of cross section 1.25 into 10 raised to minus 4 meter square. One wire is given. It is having a length 20 meter and its cross section area is also provided. It is 1.25 into 10 raised to minus 4 meter square. And it is subjected to a load of 2.5 kg. 2.5 kg is a force which is subjected to the wire. The elongation produced in the wire is 1.4 into 10 raised to minus 4. This is the value of small l. Calculate the Young's modulus of the material. So first let us write down the given things. Wire is having a length 20 meter. Area of cross section is 1.25 into 10 raised to minus 4 meter square. Force is 2.5 kg. It is given in kg. You'll have to convert it into Newton. So you just have to multiply it with 9.8. Mass into gravitational acceleration. 2.5 into 9.8 is the value of force. Small l, elongation produced in the wire, is 1 into 10 raised to minus 4. Then by the formula of Young's modulus, F into capital L upon small l into A. Just substitute the value of F. It is 2.5 into 9.8 into 20 is the original length, into 1 into 10 raised to minus 4 into 1.25 into 10 raised to minus 4. These two 10 raised to minus 4, 10 raised to minus 4 will become 10 raised to minus 8, and when it comes in the numerator it will become 10 raised to 8. Then we are having 2.5 and 1.25. So when you cancel it, 2.5, it will become 0.5 in the denominator. 9.8 into 20 divided by 0.5. Here similarly, when we cancel this 5 with 20 in the numerator, it will become 40. 9.8 into 40, this answer will be 3.92 into 10 raised to 10 Newton per meter square. Newton per meter square is the unit of Young's modulus, because Young's modulus is the ratio of stress to that of strain. So only stress will contribute its unit, as strain is not having any unit. So hope you'll have understood these two examples. In the next lecture, we are going to study two more modulus of elasticity. Till then, thank you.